Hi everyone. So today, let's talk about making change happen. It's election season here in the US, and many of you may not be happy with your party's candidate of choice. So I'd like to offer you some candidates that are all about change. They are... I didn't build in any hold for applause or anything. So they are Unix, Sed, and Grep, and together we can change anything. I'm William Smith, and I work for Jamf. You can find me on in most forums and social media as Talking Moose. If you'd like to test out the code snippets that I'm going to be showing you today, you're going to find them on my GitHub Gists page. You can scan the barcode, or you can go to jamf.it/ASG for Unix, Sed, Grep. I'll also show this QR code at the end. Let's start off by talking about the battery in your laptops. It's a smart battery. And by smart, I mean it has some intelligence built into it to report things like its health. I can report on a smart battery's health using a command line tool called IOReg. So let's see what that looks like here in Code Runner. I'm going to type out my IOReg command and filter for Apple Smart Battery. And then when I click Run, it gives me a long list of attributes and their values, and this is what I'm looking for here at the bottom. It's cycle count. My battery has cycled through the equivalent of 116 full battery charges. That's a great indicator of health because Apple says that most batteries today have a maximum cycle count of about 1,000. Then it's time to replace your laptop. So my laptop's nowhere near the end of its usefulness. I want to report on the cycle count in my management system, and specifically, I want that 116 number. I need to whittle down all this information, so I turn to my old standby Grep. I'll pipe the output of my IOReg command into Grep, and I'll tell it to give me all the lines that contain cycle count. When I run that command, I see what I'm after at the end of the output. That's great. Now, how do I get just that 116 number without that cycle count equals? A quick Google search along with some trial and error, and I come up with an awk command that seems to work. So I'm going to pipe the output of my grep command into that and print $3. I run the command, and behold, I have just the number appearing at the end of my output. That's exactly what I'm after. But I still have all this junk that's coming along for the ride, so how do I get rid of that? Well, one thing I noticed is that all this junk is between curly braces. How do I get rid of everything between the curly braces and the curly braces themselves? So I Google to the rescue again, right? I find a sed command, it's short and sweet, and all I have to do is modify it just a little to look for those curly braces, and then again, I'll pipe that out from awk and run that. And that's exactly what I need. So there I've got it, Unix, Sed, and Grep working together to give me the information I'm after. What more could there be for me to say, right?
Thanks for coming.
So I'm actually here to help you today not to write something like that. When I look at what I've done, I see two fundamental problems. I consider one of them to be much more important than the other one, though. The first thing someone who's been scripting for a while might point out is that this is kind of inefficient. I'm running a total of 4 commands here. The IOReg command to give me the information that I need, and then 3 more commands just to delete the data that I don't need. Now, don't worry that you can't read this. That's not really that important. Truth be told, I could have used just awk, or just sed, or just grep to do the same thing. And if I used a slightly different and shorter IOReg command, my grep commands can even get shorter as well. So fewer commands improves efficiency, right? Now for folks who maintain or who measure their success of the commands by how short they are, I submit that they're being a little disingenuous these days. I often hear them say, fewer commands means I'm saving processor time and processor power. And that's true. But how important really is that? NASA sent men to the moon in 1969 with a guidance computer running at slightly over 12,000 flops per second. A flop is a floating point operation. So think of it as how fast your computer can number crunch. So 16 years later, in 1985, the Cray 2 supercomputer was the fastest computer in the world, and it was running at 1.9 billion flops per second. That's a huge leap over 12,000. That's a 2 followed by 9 zeros. And it was the first Cray computer to run Unix, which we're all running on our laptops today. And nearly 20 years later, in our pockets today, our phones are running something Unix-like, a Unix-like operating system, on processors that are thousands of times faster than that Cray 2 at 2 teraflops per second. That's a 2 followed by 12 zeros. High-end laptop computers are running close to twice that speed at 4.6 teraflops per second. And that's just a personal computer. That's not even today's modern mainframe. And we're still getting more powerful when we consider gaming systems such as computers. So Microsoft's Xbox Series X systems are running at 12 teraflops. And to round out this list, the United States Department of Energy is running a modern Cray computer, HP's Frontier, which in 2022 was the world's fastest supercomputer, running at 1.1 exaflops. We're just completely skipping petaflops at this point. An exaflop is a 1 followed by 18 zeros. So guess what it's running? It's a souped up flavor of SUSE Linux. If we look at all these computers with the exception of the Frontier, which is somewhere up on the roof somewhere, we see that processor speed these days for what we do as administrators just isn't as important as it used to be. NASA's guidance computer got the job done. It was enough to fly the astronauts. It wasn't enough to fly the astronauts any faster to the moon. It still took them 3 days just to get there. But these days, it takes milliseconds to run commands when we're doing all the calculations locally on our computers. If anything's going to speed up our scripts or affect the speed of our scripts, it's going to be the network. Things like curl commands, where we have to reach out across a busy network and we're dependent on the remote server and its responsiveness. So while it's not a bad practice to be as efficient as possible and have as few commands as possible, processor speed today isn't really a good reason anymore. We're simply not bound by hardware. So what is a good reason? Let's take a look at that IREG command I put together and the number of charging cycles. Here's why you want to reduce commands. Every command you introduce is a single point of failure, or every command you introduce becomes one more variable that you have to troubleshoot when your script doesn't work. When writing scripts, you sometimes need to forget the big picture and pay more attention to the details. Normally, we'd say it's a bad thing when you can't see the forest for the trees. But what about when you're way up here? Should you really be focusing on the big picture at the moment, taking in the scenery? Sometimes that's not what you should do. And I think that applies to script writing. Author Chuck Palahniuk says, the trick to forgetting the big picture is to actually look at everything up close. Don't concentrate on how big the problem is. Take one step at a time and make sure you get it as right as possible. Many steps done well now will let you enjoy the big picture later. My goal for this presentation isn't to read you the man pages for Grep, Sed, and Grep, but rather to teach you how to fish. Some of you may use these tools every day, and others of you may only use them just once in a while. I think it's important to understand why Grep, Sed, and Grep were made in the first place. Knowing that might give you some understanding into why they behave the way they do. If you've ever used them in your scripts, you know the syntax for writing them can be confusing. But you might be surprised at a few things that they have in common with each other. When you know how they're alike, then you'll get a better understanding of when you'd use each one. And I'll show some examples and talk about their syntaxes. It's very important you understand what you're doing or what you're looking at so you can practice the art of script wizardry instead of script sorcery. So now, let's travel back in time to just before the Unix epoch. Not ed, ed. The most user-hostile editor ever created, says computer historian Peter Salas. Next month, August 2024, ed turns 55. Here in the US, that means it can qualify for the senior citizens discount at McDonald's. ed was written by this man, Ken Thompson. Does anyone know who he is? I see some heads nodding. He's one of the co-creators of Unix. Ken is 81 today, and he is still with us. And if you do the calculation, he wrote Unix when he was 26. Is anybody here under 26? You've still got time. ed is the first text editor ever made for Unix, and it's available on practically all Unix systems. It's on your laptops right now. So why does ed have this reputation as being user hostile? Well, let's find out. I have terminal running, and this is an example from ed's Wikipedia page. So to start ed, just type into terminal ed and press return. I'm in ed now. All ed commands are single letter characters, so I'll press A to append. Then I'll type a couple of sentences. ed is the standard Unix text editor. I type slowly. This is line number 2. All right. Now, I type a period to exit append mode. Of course, why not type period to exit append mode? Now, I'll type 2i. The I means insert. Apparently, append means insert at the end. So, and the 2 means I'm going to place my cursor, if I had a cursor, at the beginning of line 2 and start inserting there. I'm going to insert a blank line, and then I'll type period again to exit insert mode. Now, I'll type comma L. I'm telling ed to display or list what I've typed so far. And there you go. You might notice all of my lines end with a $sign. That's to let you know that's the end of the line. Now I'll type W, text. W means write, and text is the name of a file that I'm going to be writing to. That's how I save my work. When I press return, ed writes the file to my current folder, which is in my home folder, and if I were to look there, I would see that file now. And notice ed actually gives me some feedback. For once, 63. That's the size of my file in bytes. So let's keep going. Remember, I inserted the blank line before line 2. That means line 2 is now line 3. I need to fix that. I do that by specifying I want to do something to line 3, and then I type a substitute command. And remember, ed commands are all single letters. So I'm telling it I want to replace the word 2 with the word 3. Now let's see what my text looks like. Again, I type comma L, and now line 3 says this is line number 3. Let's type W text again to write my buffer to my file and save my work. And this time I see that changing that 3-letter word to a 5-letter word has increased the size of my file by 2 bytes. I can get out of ed by typing Q to quit. All right. You just saw me type everything correctly here, but had you seen me mistype something, ed would have given me just a question mark. A question mark means error. So what do you do when you receive an error? According to some documentation, when one receives this error, the experienced user will know what to do or what is wrong. Yeah, ed seems like a pretty harsh command line tool, but why is it that way? ed was written by Ken Thompson at MIT in Berkeley, California. He also wrote the first Unix operating system, as I said a bit ago, and he wrote both on a system like this. This is the PDP-7, and here's what it looked like. So do you see anything unusual about it? Something missing, maybe?
Where's the touch screen?
There's no... I love that. Where's the touch screen? There's no monitor. Early computers didn't output to screen. Instead, they output to paper on something called a teletype, which is that typewriter-looking thing that you see to the right. And you didn't interact with computers back then like we do today. Instead, you'd write a program, probably by hand on paper first. Then you'd type your program on the teletype, where it would act like a typewriter and it would show you what you've just typed. But at the same time, it would punch a tape that could be fed back through the teletype and into the computer to program it. And if you've ever written a script, imagine having to type your entire script before you could actually run it and test it. The key point to all of this is that most computers 55 years ago were non-interactive. ed was written where it was expected to be programmed with everything it needed to do and then just simply do it all at once, quickly, so that you could get off the computer and let somebody else onto the computer so they could run their program. That's why it seems so user hostile. It wasn't designed to give us immediate feedback like we're used to today. Like our tightrope walker a bit ago, if you didn't pay attention to each step, you were in for a bad time. Those teletypes were later replaced by these. They're not computers, they're terminals. Sometimes they're referred to as glass teletypes. Unix was written to support time sharing, which back then meant supporting multiple users accessing the mainframe, giving each user a little slice of time at a time. Terminals meant that you no longer had to sit in front of the mainframe and that you could work from anywhere in the office. But press a key on the terminal's keyboard and the signal literally had to travel back to the mainframe and then come back to the terminal to appear on the screen. It could get pretty slow when multiple users were trying to use the system at the same time. What I'm showing you here is a VT100 terminal. That's a smart terminal. And it could run a program called a shell. Guess who wrote the first Unix shell? Ken Thompson. And guess what the shell was running on, or guess what the shell running on a smart terminal allowed you to do? It allowed you to run programs locally instead of back and forth with the mainframe, and it allowed you to script them. Now, everything just speeds up. And this helped make it possible for those programs to become very, very specialized. We're finally in the realm where we can interact with our data processing commands in real time, if we choose, or script them when we need to process some data over and over again. Now we need new tools to take advantage of all of this. Let's see what happened over the course of time. I've marked the Unix epoch, which is January 1st, 1970. That's the date where Unix's clock starts at 0. I've already talked about ed, written in 1969. We'll find its direct descendant is Grep, also written by Ken Thompson in 1973. Grep stands for Global Regular Expression Print, but its original name was just S for search. Remember, ed commands were all just single letters, and Ken Thompson really liked that simplicity. Now, I didn't mention it before, but ed supported regular expressions, and regular expressions is actually part of Grep's name. Now, I'm going to explain in a little while why regex is so important to all these tools. The reason Ken Thompson created Grep is that ed couldn't handle large amounts of text. It was written for systems whose buffers were really tiny. Grep was very successful, and it inspired Lee McMahon to build on it to create GRES, G-R-E-S, which stood for Global Regular Expression Substitution. Later, GRES morphed into what we know today as SED, which is short for Stream Editor. SED took a key element from ed, its substitution syntax. And if we look back at the ed command demonstration that I showed you, you'll see it here. Remember, in ED, every command is a single letter, and S stands for substitute. Here's where we're substituting the word 2 for 3. Or instead of using a literal word like 2, I could provide a regular expression and match all sorts of patterns. We're going to look at that more closely later. And awk is the successor to both grep and sed. I consider it the ABBA of the Unix world because just like the pop supergroup of the 1970s, it's named after its creators, Alfred Aho, Peter Weinberger, and Brian Kernighan. Aho, Weinberger, Kernighan, awk. Mamma mia. Whereas grep was designed to be a more powerful search, and sed was designed to be a more powerful search and replace, awk was designed to be a text processor from the beginning. What it gets from ED is its ability to run not just one-liners, but a full programming language. And from grep and sed, it gets similar regex support, including much of the same syntax for matching regular regex patterns. Awk, sed, and grep are the trifecta command line tool set when we need to manipulate all sorts of text, whether it's structured like a CSV file, log files, or unstructured like text documents. We consider all these tools as filters to help us extract the data we have and turn it into a format that we need. And if you're looking at this, you might be wondering, why 3 tools to replace just one? I can tell you it's very much in line with the Unix philosophy, something else Ken Thompson created. The idea behind it is simple. Make programs that are minimal, modular, and maintainable by someone other than its creators. It's been summarized as write programs that do one thing and do it well, write programs that work together, and write programs to handle text streams, because that's a universal interface. In other words, use plain text. Awk, sed, and grep all read plain text, and they all output plain text, which is why we can use them as standalone programs today or as part of our scripts. So awk, sed, and grep share a common origin story. All 3 of them have probably been around longer than most of us in this room. Most of us. I think that's actually pretty amazing. Sometimes I think none of us would be here right now if it weren't for Steve Jobs and Steve Wozniak, who founded Apple in 1976. But neither would any of us be in this room right now if it weren't for Ken Thompson, too, in 1969. It wouldn't be until 30 years later, in 2001, that these giants would come together and make Mac OS X. It's good to know your history because now we can look at why there was a need for awk, sed, and grep, and that they share some commonalities, which we'll look at next. When I explained ED was written and then how awk, sed, and grep were both born out of ED, I mentioned a few similarities they have in common. So let's look at those again and a few of their differences as well. And remember, awk, sed, and grep are really meant to succeed ED. So we should expect one or more of them to be able to do what ED did. First, these are all text processors of some sort, specifically plain text, which is core to the Unix philosophy. It's the common format that makes interoperability and data sharing between them possible. But out of all these tools, awk included support for numbers and calculations. If I needed to examine a CSV file that contains a list of cities and a range of temperatures for the week, I could use awk to create a list and then calculate each city's mean temperature for the week. All of these tools directly reading files on your computer as a means of standard input, but not necessarily the same syntax for commands. I think part of our frustration with understanding some command line tools is the difference in how each one invokes a command to do something. So let's look back at that example again from ED. Insert, list, write, quit. Those are all verbs, and they take action. When you act on something, it causes a noticeable change. One of the reasons ED gained its user hostile reputation was its terseness. It used single letters to represent all of its commands. We live in a GUI world today where our buttons say print, cancel, and save. They don't say P, C, and S. So we don't have to struggle with remembering whether S means save, search, or substitute. Probably why folks struggle with Sed so much is because it inherited ED's terseness. Understanding just that one thing about Sed might make it easier to kind of understand. And if I didn't make it clearer earlier, when you think about it, grep has just one command, and that is to search. It's always in search mode, so you never actually have to specify that you want to search. That's likely why it's the first tool that we think of when we need to make some kind of command line tool to process some text. We've been trained by our software today to find and replace. So for find replace, we probably want to use sed. Again, it's a stream editor. It reads in one line of text at a time and then it changes it. That one line could be part of a paragraph with many sentences, or it could be part of a book with 12 chapters, and each chapter is its own file. But when we need to get down to individual pieces of data in each line, like words or fields, that's where we want to go to awk. That's how all these tools work, one line at a time, processing it and then moving on until it reaches the end. Key to all these tools is regular expressions. I call it regex, you might call it regex, GIF, GIF, I call it regex. Regex is probably why we look at sed and awk as sorcery. We haven't taken the time to understand it. Shameless plug, I gave an introduction to regex back in 2020. You can find it on the Mac Admins Conference user channel. I'll provide the link in my notes for the session. Something else that all these tools have in common is addressing. Think of an address like your home address or your mailing address. Your address helps me find you. In awk, sed, and grep, addressing helps them find strings in the content that you're searching. Here's a quick example of what I mean. I've applied syntax coloring to make this a little bit easier, but it's really not important here. This is a function that I include in a lot of my scripts where I'm using the curl command to read Jamf Pro's API. Every time I run it, it returns a 3-digit HTTP status code. Status codes in the 200s mean successful. Status codes in the 400s generally mean an error of some kind. Sometimes in my scripts, I want to know whether my curl command succeeded or failed. But I like words, not numbers. I can understand what words mean. So I've listed about 9 of the most common status codes I might see from 000 to 500. If I receive status code of 409, I use grep to search for 409 in my list of status codes, and it returns, 409 conflict. I'll talk more in a little bit about using addressing and how to recognize addressing in someone else's scripts. Last on this list, I mentioned global by default, and notice how ED isn't global. So what do I mean by global? Simply put, a command applies to the entire amount of text you submit to it, and it will return everything that it finds, not just the first thing that it finds. Here's an example of what I mean. I have a poem with 4 lines, and remember that awk, sed, and grep are line-based tools. They'll stream my poem, processing one line at a time, return the results, and move on to the next line until they're done. Here, I have an example of addressing for each of the commands, and each one will return what you see there on the right. The address I'm looking for is Mary. I'm only interested in those lines that contain Mary. When the command finds a line containing Mary, it'll print the result to my screen. Otherwise, there's nothing to show, and it moves on. Each command is doing something just a little bit differently from the other two, though. Grep is the simplest. You give it something to search for and something to search in, my poem, and it returns any line containing Mary. On the other hand, I have to tell sed what I want it to do when it finds a match. In this case, I want it to print that line to screen. To do that, I have to specify P to print. Remember, sed inherited ED's one-letter commands, P for print is one of them. But if that's all I did, I'd get something that kind of looks like this. Instead, Sed's default operation is to print the line it's evaluating. I am working on line Mary had a little lamb, just letting you know. And if that line matches, it'll tell you that it matches. I have found a match, Mary had a little lamb. Then it moves on to the next line. I am working on the line, its fleece was white as snow, just letting you know. But if it doesn't match, it does nothing, and it moves on, and it goes like that, line by line, until it gets to the end. That's why I need to include that -n option. It's telling Sed, hey, you know what? Don't bother telling me which line you're processing next. I'm good. And with that combination of -n and P, I get what I'm really after, which are just the lines containing Mary. Awk has a superpower. To do like Grep and Sed and return every line, I need to tell it to print, spelled out, $0, which means print the entire line when you find a match. But if I replace that $0 with a $1, and then it'll not only find every line that contains Mary, it'll print only the first word of that line, 1. $2 will print the second word of each matching line, $3, the third word, and so on. Now we're seeing awk as a text processor rather than just a text editor. This list kind of just scratches the surface of how awk, Sed, and Grep are similar and different, but I think understanding them is the path to wizardry. And it should be apparent, looking at the checks and X's, Sed and awk are the two powerhouse command tools here. There's a saying that goes, when all you have is a hammer, everything looks like a nail. What I'm hoping you grasp from that list is that there can be a right tool for the right job. Sure, I can pound a screw into a piece of wood using a hammer, but it would be so much easier and so much better if I just learned how to use a screwdriver. Let's talk more about when you'd want to use each tool. To choose the right tool for the right job, we need to know two things. What type of data do we have? What do we want from that data? In a little bit, we're going to look at a few types of data that we might see in our jobs as administrators. But before we look at some examples, let's talk a little bit about structured data. It's usually easy to recognize when you see it. Simply put, we're looking to see if it's presented to us in some sort of format. This is one of the most common ways that we could receive data. It's a spreadsheet. It's the epitome of structured data. This is why this is an export from my Jamf Pro server of some computers that I have in my inventory. We have a whole bunch of these rectangles, and many of them hold some information. Some don't hold any information at all. And these spaces are called cells in a spreadsheet, but they're also known as fields. You can very literally think of them as fields on a farm. They're often next to each other. Some of them may have crops growing in them, or some of them may be fallow for the season and be empty. They're placeholders. Just because a field is empty doesn't mean that the field itself doesn't exist. We have rows going across that describe computer information. In a database or a spreadsheet, we call these rows a record. And we have 5 records giving us details about 5 computers here in the spreadsheet. We have an extra row at the top that's not a record, but headers for the columns of each record. And it may sound trivial to mention, but it's important when speaking about structured data. A spreadsheet like this will only ever have one row of headers, either at the beginning or at the bottom. Usually it's at the top. But structured data may not always have these headers, which means it's even more important to understand what your data contains. Then we have columns. In this case, we have 6 columns. The headers at the top of the columns each define a specific attribute or a property, such as model or serial number, and each cell in the spreadsheet is one piece of data. Sometimes it's called a data point. Again, not every field may contain data, but the field still exists. and no data is technically data. By itself, a data point is meaningless, but when we cross-reference it with a key piece of information in the record, like the computer name, or a property, like a serial number, then we have more than data, we start getting information. It's the information that we're after. And to get detailed information, we need this structured data. But note that I'm not telling you what the structure is that we need. The structure is actually not that important. A spreadsheet's nothing more than a table. This is the same information in the same order, it just looks different. And do you see more structure within the structure? An IP address has a structure of 4 numbers separated by 3 periods. These timestamps have a structure of date followed by time. The date itself has a structure of month, day, and year separated by slashes, and the time has a structure of 2 numbers separated by colons. And structure isn't limited to just numbers. The operating system names all begin with Mac OS, and they're followed by version numbers in semantic versioning format. Now, here's the same computer information in yet a different format, a different structure. The computer records are still sorted top to bottom, but their fields are separated by commas. And it's important to note that each record is separated by a new line character, a return, this key that you see right here. Many GUI applications will allow you today to show invisible characters like returns, but know that they are characters too. You may not see them, but Unix, Sed, and Grep will see them. Knowing what separates the data is going to be super important later. Here's yet another way to structure the same data. I hope most of you are familiar with XML. Mostly we just receive data in this format. We don't really go out and create it ourselves. So to make this easier to look through, I've applied just a little bit of syntax coloring for it. Again, our records are in the same order, but what you're looking at actually is formatted in 2 different ways at the same time. First, this XML is formatted for human readability. And what I mean by that is each computer record is indented, and each property of the computer record is indented even more. And each piece of information is on its own line. But here's how computers read XML. They don't care about the returns between records, and they don't care about what separates fields. In fact, they see XML as one long stream of data. And where have we heard the word stream before? Maybe stream editor? Sed? It's a great tool for XML. Now, I've shown examples of data in a table as a comma-separated values list and XML, and I've even shown you that there can be sub-data structures like date and time formats. There are other data structures like JSON, log files, HTML, Markdown, even camel case, where we capitalize the first letter of words and then concatenate them to make like a single string. That follows a pattern. And that's what we're really looking for, is a pattern. If we can identify a pattern, that's half the battle. The rest is just applying the right tool. If you can't identify the pattern, you're probably going to be out of luck. So which tool, Unix, Sed, or Grep, is right for each pattern? Well, to determine that, we have to know that our data follows a pattern, and then we have to decide what we want from that data. I said before that you can think of Grep like a search tool, and Sed like search and replace, and awk is what you would want for processing text beyond simple search and replace. So pretend we're looking at some data and trying to figure out if it has some kind of structure to it and what we want from it. Here are some things that we might say to ourselves. First, I don't see a pattern. Well, maybe I'm looking at a data dump of information someone's provided me, like a book or a brochure. That's pretty common in the print industry. I might be a proofreader, and I might be looking to create an index of keywords. Grep would be ideal for that because I'm only searching for words to create my index. Or I might have noticed the author commonly misspells Mississippi. Grep can't correct spelling, but Sed can. and I can search for the misspelled words and then replace them with the correct words. awk could probably do that too, but it would just be overkill. All right, next line. I'm only looking for the existence of something. That one's pretty straightforward. I want to use grep. It's simple, and that's what it's made for. I might actually find it more difficult to use sed or awk for something as simple as just seeing if data exists. Next, I'm trying to change something. That's what sed does so well. Its sole purpose is to read a stream of data, whether it follows some sort of pattern or not, find a thing and then change that thing on the spot to something else. It could be changing a word, it could be deleting a word, or maybe I see the author using a term like regular expression over and over, and I could use sed to change every regular expression to just regex. And sed's perfect for that. Next thing we might think, I'm trying to extract specific data points from my information or from my data. I can use sed very effectively as a filter, and quite often I'm dealing with XML. And remember, XML includes tags with angle brackets around its data, but sometimes I just want what's between the tags. I can tell sed, look for those tags and then give me only the data between those opening and closing tags. Good. But what if I have something like a mailing list with names, addresses, and phone numbers? And what if I want to look for everyone in Pennsylvania and create a list of phone numbers? That's when awk shines. I showed my example of awk a bit ago for all those lines with Mary in my Mary Had a Little Lamb poem. Then I showed how I could call $1, $2, $3, etc. to pull out specific words. I'll show more about that in just a little bit. I might say to myself, I'm trying to reformat this data. As I've said a few times, grep is for search, and sed is for search and replace, and awk is for text processing. That mailing list I have has all of my information stored in a spreadsheet or a CSV file with one person per row. Using awk, not only can I extract that data, I can use it to create mailing labels with the name of the person on the first row and their address below that. We'll see how that works. I might say that my data has no line breaks. All right, this one's a little bit tricky. All these tools are effectively line editors, and they need line breaks to help with the separation of data. That's why structured data is so important. Grep isn't going to be very much help. It can only return entire lines of text. If all the data is running together, it'll only be able to tell you, yeah, I found something, or nope, didn't find a thing. And that may be good enough, but that's probably not what you're after. Sed can work somewhat without line breaks. Again, think about the XML stream. Sed stands for stream editor, so it's made to work on streaming, something like that. But if you can feed it structured data, and with each record separated by a return, then it's going to be a lot more powerful. And awk is really only useful when you have line breaks. So my advice to you here is structured data, structured data, structured data. We really want data in a standardized format. You're probably thinking by now, Bill, that's all well and good, but what I really came here for was all the code snippets. Can you just show me the code? I'm going to give you several examples next, but keep in mind, I've talked about 100 slides. I've talked for about 100 slides so far, and I've already given you the information that you're going to find most useful, which is you want to determine the right tool for the right job. If you're planning on learning any of these tools in depth, you're still going to Google much of this information. But if you're planning to use these tools day in and day out, I highly recommend learning from books and following their step-by-step examples or taking an online class. You really want to immerse yourself. I personally love physical books, like this one right here. And the ones that I love are from O'Reilly. They are the de facto publisher of technical instruction guides for computers. And you know what? They really don't go out of date. This one's from 1990. Granted, it's been updated a few times. awk has been updated a few times. In fact, there's even a second edition of this to catch up. But everything in here is still as valid as it was today, as it was back then when it was written. And as I said, these command line tools are nearly 50 years old, so you're not going to go wrong with buying your books from a used bookstore. Save the planet. Before we get into some code examples, I'd like to explain a little bit about how I write my code and I script things. So let's start off with the useless use of cat. And by that I mean using, thank you. And by that I mean using the cat command to read a file and then piping that into awk, sed, or grep. Don't do that. Each of these tools can read files on their own without any help from cat. All you need to do is put your file name at the end and they'll read, they'll each use that for their input. You're also eliminating a command, which means there's less to go wrong and less to troubleshoot when something does go wrong. I kind of feel the same way about echo and variables. Echo is actually built into the shell. It's still a command, but I prefer here strings. That's what these three less than symbols are. If you're familiar with using a single greater than symbol to write something to a file, or those two greater than symbols to append something to a file, think of a here string kind of similar to that. What it's doing here is the equivalent of piping the variable into the command without calling echo. I just like this better, but I don't see many folks doing this, so I thought I would at least explain it here. And you may have noticed how I use quotes in my earlier examples. Quotes are very forgiving in all three of these tools, but there are times when you need to use the correct quotes. Looking at grep, I follow a few practices. First, you really don't need quotes around single words, like I'm showing you here in this first example for tacos. But in the second example, I do need quotes around my search string, too many tacos, when it contains spaces. And notice these are single quotes. I could just as easily use double quotes here and it wouldn't make a difference. And in the third example, my search string is actually a variable and I must use double quotes. If I used single quotes, my variable wouldn't expand and grep would literally look for $variable. So to keep it simple, I always use double quotes around my search strings. I'll rarely go wrong with that. When I use sed, I must use quotes around my search strings, either single or double. And here, I usually use single quotes. Otherwise, if there's a variable, I still need to use double quotes around my search string. And finally, with awk, I want single quotes around my print command in the curly braces. And in order to include a search string, I need to include that within my quotes, so single quotes. I'll warn you, there's going to be some nuance here about using quotes with any of these commands, but those are the rules that I generally follow. And just so we can keep things straight, let's define a few terms that identify parts of a command. These are the three commands I showed you earlier for returning all the lines containing Mary from my poem earlier. Sometimes I may loosely refer to the entire line as a command, and I don't want that to be confusing. So let's call each of these lines a statement. I'm telling the computer what I want it to do. We quite often refer to these as commands too. Each of these, grep, sed, and awk, is a binary, or a program, or an application, or a command line tool. It's a compiled piece of code that accepts instructions and it carries out an action. I'm only showing it for sed, but all of these command line tools support options, and I'll say it, options are optional. Important to know, they are not verbs. They take no action. They're an extra limitation or an extension of what the tool can do, but they're not a command. You can recognize options because they generally begin with a single dash and a letter, or sometimes a double dash and a word. This is a loose naming standard across many command line tools. But what I'm showing you here is the same option in two different ways. The first is an abbreviation and the second is the same option, but it's just spelled out. Either is going to work identically in your scripts. There's no difference between them. But do yourself and your future self and anyone else who looks at your scripts a favor. Whenever possible, use the full name. It's readable and it's understandable, and you don't have to guess later what it meant. Feel free to use the abbreviation when you're typing stuff manually into terminal and you just want to save yourself a few keystrokes. Earlier, I talked about how we're using the word Mary as a search term or an address. This is what I'm telling my command line tool to identify in the data that I'm giving it. That's the text Mary, but the term for this is pattern. It's a string of characters I'm telling my command line tool to match, and if it finds a match, to do something. To keep these straight, think of it like this. I live in apartment 1A, that's my address, or it's my search term, but the pattern is a number followed by a letter. And patterns support regular expressions. Here, I've replaced the middle letters with a dot followed by an asterisk, which means 0 or more characters. Now my pattern might match Mary, Marty, Misty, or magnanimously. Any single word that begins with a capital M and ends with a Y, a lowercase y, is going to work. So up to now, I've been defining what to look for in my statements. Now I need to say what to do. Toward the end of my statement is the command. And remember, this is a verb. This is where we say what action we want to take. And when we can only take, and we can only take one action at a time, not multiple. And you'll notice that each command line tool has a different way of invoking a command. I mentioned grep is short for global regular expression print. The print command is literally built into grep, so there's no need to actually tell grep to print. Sed takes after ed and uses single letters for commands. We've talked about the P, meaning print, which means display on the screen. But other common commands include delete, write, append, insert. Some of those are directly from ed. Awk, for the most part, has pretty much one command, and that's to print. And you'll always find it inside curly braces and single quotes like you see here. But its print is pretty powerful. We can tell it to print $0 or the entire line that was matched by my pattern. Or we can tell it to print $1, $2, just the first word or the second word of that entire line that matched my pattern. We can tell it to do math, add 10 to 20 and print 30. And it can even handle variables. In the first set of brackets, I can do something to like assign variables 10 and 20 to variables A and B. And then in the second set of brackets, I add those variables together and print 30. It's the commands that produce the results or make change happen. And again, they are all verbs. Verbs show action. The last part of any of these statements is the input, the data that we provide to them to process. I mentioned earlier that grep, sed, and awk can all read lines. You just need to add the path to the file at the end of the statement. And I discussed how I like using here strings. Those three little less than symbols that let me use a variable from earlier in my script as input. This is what I prefer, not only to avoid using something like cat or echo commands, but it allows me to always have my input at the end of my statements. I like that for consistency when I'm looking at my scripts. Altogether, awk, sed, and grep will generally follow a formula. I invoke the name of the tool of the program. I provide any options that I need to limit or extend what I'm doing. I give it an address. That's to tell it to look for some sort of pattern or something that's going to follow like that. I call the command to tell it what to do. And at the end, I specify the input data to act on. All right, so let's look at some examples here. We'll start with grep. Here I have some XML about Apple Watch models. There is an XML tag on the second line of each record called model name. I want to pull all the model names from my XML. I grep model name and I feed it my XML. It returns 2 lines. That one's simple enough. All right, let's look at another one. Grep has an option called after context, which just means I'm looking for some line that's after the one that I found. In this case, I want to get the display name of the Apple Watch too. And the display name is always on the next line after that model. So my option is -- after context 1. The 1 means 1 line down. When I run my statement, I get not only the line that matches my pattern, but also whatever follows that pattern. And I'm not limited to just one option. I can use multiple options. So not only can I use my after context option, I can add another one called line number. It prints the line number of the matching lines. So here, I've matched lines 2 and 3, as well as 6 and 7. Grep's not difficult to use for finding information. It's always going to follow the syntax of program, then options, then pattern, then input. Now let's look at Sed, and let's look at one of its core features, which is substitute. In ED, I showed how it could substitute the word 2 for 3. Sed takes that exact syntax. Here, I have a list of Apple Watch models. I'm no good with model identifiers. I need words. So I want to substitute the model identifier with its actual display name. This is Sed's syntax for that. It looks just like ED. So I write my statement like this, and it works for me. All of these, though, are Apple Watch Series 9 models. Why not change them all? So I can do that in a few ways. I can use semicolons between multiple substitution commands, like you see here. And remember, these tools can only do one command at a time, but nothing says we can't string a whole bunch of them together. But when you start repeating things with slight changes, as I'm doing here, consider that there might be a better way. And here it is. How about this? All I've done is replace the line number, or replace the number 3 in the watch 7,3 pattern with a regular expression. A \D means any single digit. That's a lot easier to understand and a lot easier to troubleshoot if something goes wrong. But you need to be familiar with regular expressions. Now I've left this search and replace command for Sed on the screen because I want to talk about the Sed elephant in the room. And it took me many years to notice this, and it caused me a lot of confusion until I learned Sed got this from ED. Does anyone see it? Is that what you were thinking? All right, let's look again at the order of the items in the command statement. In this substitution for Sed, the command is now before the pattern. This is the exception to the rule, not because there's a reason, but really because its substitution syntax is a legacy inherited from a 55-year-old program. Every other Sed command follows the normal order of items in a command statement. If you remember one thing about Sed, remember this. Otherwise, Sed commands look more like this. A pattern is always between /, a single letter command follows, and the whole thing is wrapped in quotes, single or double. It usually doesn't matter unless you're dealing with variables, whether it's single or double. Here's a short Sed example that does a couple of neat things. So first, the 2,4 is a different type of address. This time, instead of referring to a string or a regular expression as a search term, I'm using numbers to refer to line numbers. I'm not trying to match a pattern here, so I don't need to enclose it in /. And not only that, I'm separating these numbers with a comma, which creates a range. So here, 2,4 means 2 through 4. And after that, I add my command D for delete. It's really simple. And when I run it, lines 2 through 4 are removed from my output. And if I change the D to a W for write, and I provide a path to a file, Sed does two things. First, it outputs to the screen every line it evaluates. And remember, Sed's just letting you know what it's doing. But at the same time, it's creating a new file called numbersfile.txt, and it's populating it with lines 2 through 4. Sed can do a lot. And if you're likely going to be doing you're likely going to be doing a lot of Googling to find the right syntax for what you need. Keep the concepts of options, patterns, commands in mind when you're reading examples, so you'll be more likely to understand what you're actually looking at when you do find something. Finally, let's look at some things that awk can do. It's ideal for working with tables of information like an address list. I've said a couple of times, I can use it to look for something and then pull out pieces of information and then rearrange them into a new form. I mentioned mailing labels earlier. And here's my mailing list, one person per line, along with their address, state, city, and postal code. My goal is to create mailing labels only for the people in California. Here's what I tried first. Each piece of information looks to be separated by a comma, so right after awk, I added an option, -F, which lets me specify that commas are going to be separating my pieces of data in each record. I'm going to break each line into pieces where I have commas. Then I include an address where the pattern is capital CA for California. I'm telling awk to only print those lines where recipients live in California. Awk commands appear within curly braces, and notice I have multiple commands following my curly brace. And I've put them on multiple lines just to make it easier to read. Because this is structured data, $1 always corresponds to a person's name. $2 is their address. $3 is the city. $4 is state. $5 is postal code. Then I close my curly braces and I use a here string to input my mailing list. Let's see what that looks like when I run it. All right, good first start. I see my pieces of information are pretty much in the right place, but I don't really care for how the address fields are indented. Let's see what's causing that. Let's see if we can try to fix it. The problem is that most of the fields are separated by a comma followed by a space. But I see there's only one blank space between the state and the postal code. And I'd really like to have the comma between the city and the state in my mailing list, but I'm already using comma as my field separator. What to do? Well, here's where a little bit of help from Sed might come in handy. I'm going to change my field separator. Look at the Sed statement between parentheses. I'm going to substitute every comma space, that's my pattern, with a tab. The \T is the regular expression for tab. And the G at the end means global. If I didn't specify that global flag, Sed would only change the first occurrence of comma space in each line, and it would ignore the rest. I'm using a here string to input my mailing list variable into my Sed statement, and then I'm taking the entire results and I'm putting them into a new variable called fixed mailing list. For my awk statement, I have to change my here string to use the fixed mailing list variable that I just created. Now, I'm not going to change anything else yet. I want to see what happens. Oh, that's not right. I didn't change the field separator in my awk statement. I'm still using a comma, and I converted all the commas to tabs. So let's change the comma to a tab, \T. All right, now let's try this again. All right, this is a lot better. I don't have those weird spaces at the beginning of my lines anymore, but I do see my city and my state are kind of running together. Let's fix that. $3 is my city, $4 is my state. I'm going to add a comma, plus a space and quotes between them. Now, let's see what we get. And that's near perfection. I think the only thing I want to do is make it a little bit cleaner. I want to add a space between each mailing label now. So I'm going to add another print statement at the bottom where all I'm doing is telling awk to print an empty line. And that's more like it. This was a good example of showing you how you can use awk to not only find specific lines containing your search string, but then using it to further rearrange the elements in a different format. And it was also a good example of taking a step back when you realize that your data structure isn't really the way you thought it was structured in the first place. When I saw all those spaces at the beginning of the address lines, I knew I could have used something like sed later on to delete all those blank spaces, and I'd be fine with that. But it pays off sometimes to see whether or not there's other patterns that you could be looking for instead. If you're familiar with scripting, you're probably familiar with man pages, the documentation for command line tools. I tell my customer that there's two types of manuals. Those that tell you, here's a button and here's what happens when you click that button, and those that tell you, here's how to do what you want. I hope you see today merely as the introduction to the second kind of manual. So to conclude, I've got stickers here for anybody that did not get one as they walked in. Feel free to pick them up as you go out the room. I would appreciate your endorsement for awk, sed, and grep as candidates for change. And please let me know if you found this session helpful. All right, let's turn up the lights and see if anybody has any questions. No questions. All right, we got one back here. Anybody got the box? On the other side. There it is. Hold on. Somebody catch this. I have no idea where it's going.
So my question is, can you go back a few slides? Because when you were going through the what ed, awk, sed, and grep could do, I was trying to just chart it out for me.
What are you looking for specifically?
That table that you have with ed, awk, sed, and grep.
Okay. Oh, all right.
It was a little farther back. I kind of.
Let's see. Tell you what, these will be posted up on Mac Admin Slack. Will that be good enough? Are you looking to take a picture, or do you have a specific question about it?
No, I mean the post would be fine. I was just looking to take a picture of it.
And I can give you a copy of my slides.
Okay, cool. Yeah. Real questions.
I'm just wondering, you gave us a bit of the history of the programs, and they
I love
all
history.
rely on regex.
Okay.
When did regex happen?
Oh, I know that one. And I don't have a good reason for this. 1951. It was developed in 1951. And I have no idea what it would have run on. But I know 1951. So maybe next year, who knows?
Regex. Yeah. 51. Was there something else? I thought.
All right, thank you very much. I appreciate it, everybody.